Just to introduce the aeronautics program at the CSIR, we are approximately 50 engineers. We host the largest suite of flight simulation facilities or wind tunnel facilities in the Southern Hemisphere. And when we speak about the defense programs that our Department of Defense have championed over the last 50 years, we have a lot to be proud of. It is really an honor and a privilege to work in this sector, in this industry. And thanks to the leadership and guidance of Mr. Rahman and his team, Colonel Miller, who's been the champion for the Aeronautical Defense and Evaluation Research Institute. But to sum up what we do, we perform all the aerodynamics research, testing and evaluation on missile systems, helicopters, fighter aircraft, and commercial aircraft as well, obviously. We do simulation, we do gas turbine development. Anything that flies, that's our passion. We can simulate anything from very, very low speeds to up to Mach 4.3. 4.3 times the speed of sound, it's approximately 5,000 kilometers per hour. Someone from the Northern Hemisphere will always ask, what are you doing with that level of technology in the Southern Hemisphere on the tip of Africa? And you see the programs that Mr. Rahman spoke about, that's what we're doing. We always punch above our weight. Every morning, we pay obeisances to the Mirage F1 parked outside our building because we're passionate about everything that flies. So that's who we are. So my talk is, I've chosen approximately 3 topics. At any point in time, we've got about 50 projects that we're managing. I can't give you a brief on all 50 projects in the 10 minutes I've got left. But I just want to give you a flavor of what we're doing on a daily basis so that we can stimulate discussion afterwards and encourage you to visit. So I'd at least hope that you opt for the latter, at least, to visit us on site and look at our facilities. I've chosen 3 topics in line with Mr. Raman's theme, which was how to challenge best practice for aerospace systems design. Then I will diversify a little bit. How do we diversify these technologies developed for other applications in other sectors, so commercial aviation? And I'll speak about unmanned systems if we get some time. It's a very contentious topic. And when we get there, I will remind you, Chatham House rules applies. It's my personal opinion. But it makes for interesting discussion and debate. Aerospace systems design and challenging best practice. If one considers a traditional fighter program, traditional aircraft development program, we look at the Airbus A380. Development cost is of the order hundreds of billions of rands. Hundreds of billions. Missile development program, tens of billions of rands. Aircraft, commercial aircraft, small aircraft, of the order of billions of rands. But at the same time, these large budgets required to participate in the sector limited to very few countries in the Northern Hemisphere. There are very few countries that have these large budgets. At the same time, we want to exploit the benefits of working in aerospace and defense because there are lots of spillovers that happen. The country benefits from a technology base. There are other sectors that are benefiting from those technology benefits, and there's jobs created. There's growth through the GDP. So South Africa has been involved in aerospace and military aerospace for a long time, but we want to use those benefits to build the economy, to build the GDP. So we still have that ambition to participate in aerospace, but how do you do it when budgets are being cut? How do you do it when these large budgets, tens of billions, hundreds of billions are required to do these programs? And it means doing things differently. If you look at military fighter program, the Americans on a fighter program will spend about 16,000 hours in a very large wind tunnel facility. And a facility that needs about 100 megawatts of power. Now think about it, 16,000 hours at 100 megawatts of power consumption. That's a huge program. A program like that is not accessible to South Africa. We can't execute that type of program. But yet we have produced products that are competitive. If you look at the life cycle of a development program for a missile or for an aircraft, everything marked experimental test and evaluation is where we need to do ground-based flight simulation. So not flying the actual aircraft, but flying it in a simulation in a wind tunnel facility on the ground. Look at how many blocks you require to do this technology de-risking. And that raises the cost. So what we've done at the CSR is we've investigated a method to reduce the number of test points you actually need to qualify a system. The traditional method is, you think about an aircraft or a missile, the job of any airborne system is to deliver a payload with a particular purpose, whether it's a missile, delivering a warhead, weapons payload, or a passenger aircraft carrying hundreds of passengers and lots of bags to a foreign destination. The purpose is to wrap around an airframe around this payload. And there are infinite possibilities to wrap that airframe can have in terms of shape, in terms of size, in terms of weight. But at the end of the day, we want to perform the function with the lowest cost, the lowest amount of time, and what does that shape look like? If we vary each individual variable that has an impact on that shape, we're talking the design or optimization of this aerodynamic shape, and we've got Carla Ubink who's doing her master's on optimization, you will have a very large matrix of test points. And you'll be testing in the wind tunnel and doing simulations until you're blue in the face. And South Africa can't afford that, where you vary one variable at a time and you vary all the others. So what we've done is we've developed this technique called modern design of experiment. And we've applied it to aircraft design. We've applied it to weapons integration. South Africa prides itself in being an independent weapons integration capability. It has that capability. Let's look at the example of integrating a store onto an aircraft. You have to clear the envelope with all these variables. The store mass and physical properties, so the aerodynamic shape. They eject all the uncertainties and range of values for the ejector release unit. The aircraft flight conditions, stations on aircraft, neighboring stores. That particular program in a wind tunnel facility is of the order 200 million rand. We can't afford something like that. What we need is something that is an order of magnitude more cost effective. And that's what we have done at the CSIR. We choose our design points, our test points very, very carefully using this technique called modern design of experiment. So we don't have to test for 120 to 200 million rands worth of wind tunnel testing. We do just 5 to 10 million rands of wind tunnel testing. We combine the benefits of simulation in a computer system. Instead of just doing everything in a wind tunnel test, we do some accurate simulations in the computer environment. We combine those two together, and we can do a flight clearance. So we can clear the envelope for carrying weapon systems, for carrying drop tanks, for carrying payloads safely with a tenth of the cost. If you look at the Joint Strike Fighter program, even the Americans are struggling with budget. This is an example that they used to demonstrate the traditional approach, which is all these test points of the store under the aircraft. This range of test points, we can reduce that matrix of test points by 1 order of magnitude. So we don't need to test all in that entire area, we just test there and there, and we can achieve a tenth of the cost. So it's tried and tested. If you look at a new aircraft configuration that's got some fancy aerodynamics that is necessary to achieve a particular mission, you have quite a lot of variables. And South African companies, small companies, startup companies cannot afford that level of cost and investment. South Africa needs a different solution. And we've applied this to an industry partner. So we've reduced the cost significantly. We've made the cost accessible to them. And that's important. Moving on to another example of how we've applied traditionally defense technology to the commercial space. We were working with a consortium of partners looking into hiring aircraft configurations for the future. So we'll look at commercial travel. There's lots of demand for global mobility. People want to travel, whether it's for tourism or for business. People want to travel and people need to travel. Within Africa, there's an increased demand for travel, regional mobility, moving across countries quickly, so we can enable families being together. We can enable increase in the quality of life. We can increase economic opportunities. We need to travel in the region more. But at the same time, there's increased pressure on natural resources and climate change. People want faster, cheaper, lower environmental impact, and more comfort. Everyone wants to sit in a business class seat. And how do you do this with the traditional ways of approaching aircraft design? So this particular consortium, we were invited to participate. It's a European Union consortium, and they looked at novel configurations for the future of air transport. What does future transport configurations look like? And so let me move on. And we partnered with a university in Portugal, Italy, Bristol, and the DLR, which is German Aerospace Institute, Embraer, KTH, and the CSIR. We all partnered to come up with a program to investigate what these future technologies should look like. The university partners came up with some very novel, very innovative, very different configurations, and Embraer came to the party and said, no, we will never manufacture this in the next 10 to 20 years. We will stick with conventional. How can we incrementally change conventional to get benefits of reducing fuel? And there are two approaches to that. One could say, if our future depends on what we've done in the past, this statement was made by someone from Airbus, Mr. Jan van Toor, who spoke this morning, and he says, if it depends on what we've done in the past, then we are limiting ourselves drastically. We have to do things differently. But at the behest of Embraer, we stuck with the brief, which was to modify what the current configuration is. And Embraer came up with this particular configuration. The CSIR did all the wind tunnel testing, all the sensor development for this aircraft, all the model manufacturing. Just to give you an idea, this test section or flight simulation test section is approximately 1.5 meters by 1.5 meters. And that is, and in this particular facility, we can test up to Mach 1.4, which is 1.4 times the speed of sound. And we tested this aircraft in that facility. And let me show you what the results were. From a computational point of view, they did some initial calculation. They said, if we change some wing configuration, we can get up to 10% increase in range, just with a simple modification of the wing geometry. Embraer said, that's not simple. We will never manufacture something like that. So they said, if we want to design an aircraft that carries 113 passengers and travels 2,300 nautical miles, we would want to modify the following. Just the leading edge and some trailing edges. And let's see what we can get out of that. And what the study revealed is, with some basic, because I'm trying to fight for time. There we go. They were able to modify the aircraft configuration with those limited number of variables to save about 5%. And that's incremental innovation. That's what came out of the program. So CSR participated in this program, that's what we saw. But this is only the start. What we envisage in the future is to be more controversial, to be more innovative, more disruptive. Can we achieve a 40% saving in fuel for the same distance travel? And the answer, I believe, has to be a resounding yes, because if we can't do it, we cannot meet the demands and constraints of the future. And that particular program, so those changes, those studies that were done with the European consortium can be applied to UAVs, business jets, and long-range commercial jets, but not really applicable for small aircraft because of space constraints. But that's exactly what happened in that program. Now I want to move on over to the next subject, which is UAVs. I'll tell you why it's my favorite subject, because everyone has a view, or everyone's an expert on UAVs. And my personal view is that the entry barriers for small UAVs have dropped significantly. If you go to the toy shop today, you can pick up a little copter this size, a quadcopter, that you can control with a little joystick, and kids of 5 years old are playing with those things today. If you go to, there are so many exhibitions worldwide on small UAVs. So small UAVs are proliferating around the world at a rapid rate. Autonomous flight is a reality. Not now, 40 years ago. This happened a long time ago. So it's not new. But since 40 years ago, there have been lots of advances. Ongoing payload advancements, meaning that the payload that goes on, whether it be sensors, whether it be weapons payload, they've advanced a lot. There are thousands of commercially off-the-shelf systems available for constructing a UAV. You do not have to be a military company owning proprietary military technology to build a UAV. There are people building small UAVs in their backyard. So there's reduced entry barriers in some classes, but for niche applications, for military applications, there's still very high cost, high complexity, very high entry barriers. And South Africa has been developing UAVs for many, many years. So it's not new to South Africa. But my view on where our focus as South Africa should be on UAVs is we should understand the entire problem. I remember on 702 a few years ago when the Rhino problem was first on the news. There was a caller that called in and said, look, the Americans are using drones. You just buy yourself a few drones and the Rhino problem will disappear. We are 3 years later and the Rhino problem hasn't disappeared. It's understanding the entire problem. A UAV in the sky will not solve your problem if you're not addressing the right things. Does your UAV tell, so from a reconnaissance point of view, let's talk reconnaissance. The importance, the UAV is just a platform, it's just a carrier. The important payload on the UAV is the sensor ball that goes onto the UAV. And can that sensor ball tell you whether that object 5 kilometers away, is it friend or foe? If it's, is it carrying a stick or is it a rifle? Can you confirm that it is a threat? That's what the important question is, not what the platform looks like. It's what that sensor system can do. So it's what that system can do that's important. How does that system integrate into a command and control structure? Yes, it's fine to fly a UAV, but does the commander have control over how he uses that asset? How the information coming off that asset is being used to make decisions? That's the important question. Anyone can put a UAV in the sky, but can we make decisions, good decisions, based on what that UAV is seeing? And can we buy the right UAV? You can have a catalog of UAVs this big. Which one do you buy for your particular application? And how do you bring it into service? How do you train your people to use this UAV? As if it's not a, in military terms, we're not talking small cost. A UAV is not necessarily cheaper than a manned aircraft. So we have to understand that. There's a video that I would like to show. And it's a real-time tracking of multiple entities in an operation called Operation Red Flag. Now, you might have seen this video before. So you've got sensors on each of the airborne assets that's tracking the aircraft or tracking the entities in that battle space. So battle space is quite complex. And I just want to let it run for another half a minute. So you've got multiple entities, lots of capability, lots of data coming to the command center. And how do you control this entire environment? Now think about inserting an unmanned system into an environment like this. You have to train for it. You have to decide. You have to simulate doctrine. You have to simulate tactics beforehand. You can't have an exercise like this and decide, okay, let's get it up into the air and let's decide then and there what we do with our UAV. So the challenge with UAVs is how we bring that into service. Concept of operations. How do you use that asset? What performance must that sensor have? Does having a manned aircraft with a big ball, does that serve the purpose better than having a UAV with a ball this size? I'll go with the manned aircraft. Colonel Miller and I have had discussions about that. Data management, you've got all the sensor data streaming down. What do you do with it? Can you make a decision any better? No, you can't. There's tons of data coming. How do you derive information and make decisions on that? That's important. Damage tolerance for hostile environment. We work in contested airspace, we work in small arms fires, no longer conventional war. How does your UAV survive that? Endurance and mass and time and distance is always a problem. So aeronautical technologies work there, but the other aspects I've spoken about are the issues. So we talk about South Africa being competitive, talk about South Africa being effective with the budgets we've got. You cannot afford to procure an asset that is not suited to the application. You think very, very hard about this beforehand. And I think, General Barker, that's my 2 cents.